Okay, well, my name is Bud Tribble, and I work at Apple Computer. I'm going to sort of take off where John left off and talk about Mac software. It's really hard to talk about history, especially if you've been involved, because what you're really getting is one single perspective on what happened. But I think that's actually useful in some cases as long as you understand that's where it's coming from. So I'm going to give my particular perspective on a lot of things. Also mentioned that it was striking during the last talk, which was all about the culture and the people. And I really believe that the culture and the people are the most interesting part of the story. And a century from now, the technology part of it will be taken for granted by everyone, and a lot of the technology already is taken for granted. But the interesting part that will remain will be the stories and the culture and the people that happened at that time. Reminds me of a book I just read called, I think it was called Longitude, about the invention of the chronograph. And of course, we all take watches for granted, but the people stories and the cultural lessons you can learn from it are the interesting part. At any rate, I will also spend a lot of my time talking about the technology and how it impinged on the culture and vice versa. Just a quick, how did I get involved in this story of the personal computer and the Macintosh? I grew up in the 60s and the 70s. I went to college at UC San Diego and got very involved in computers during that time. I'll talk a little bit about that with a good friend of mine called Bill Atkinson, who ultimately went to Apple and talked me into going to Apple, although at the time I was in an MD PhD program at the University of Washington. And I took some time off to go to Apple, and what I did there was to become the original manager for the Macintosh software project in 1980, which was just getting off the ground then under a fellow named Jeff Raskin, who I had met earlier at UCSD. And what I'm going to talk about is some of what went on in those early days and sort of what our thinking was about some of the design decisions. And I think that'll be interesting. After being at Apple for a while, going back to school, finishing my medical degree and PhD, and coming back to Apple in '85, I left along with a number of other people to found a company called Next Computer with Steve Jobs. And so the next thing I'll talk about is Next Step and the software we did there, because it turns out that ultimately that company was merged back into Apple, and a lot of the technology that came out of Next and Next Step became what is known today as the Macintosh operating system, or Mac OS X. So those three threads are kind of represented here, and I'll go into some detail on them. But before I do that, I want to spend a little bit of time putting some context around this. And one of the most important things about computers during the last few decades is that computers are just starting. The very first computer was within the last, middle of the last century. So this is a very young science. Computer science is a very young science. Just to give you some other examples, physics. 1687 was Newton's Principia Mathematica, sort of the founding principles that became physics. Again, chemistry back in 1789. Biology you can sort of date to 1735. By contrast, computer science is an extremely young science. The book that I sort of grew up on was Knuth and the Art of Computer Programming. But this idea that we're in such early days that not only do you not know what the potentials are, you don't know what the limitations are. And this really pervaded a lot of the hacker culture and the early people like McCarthy and others who got involved in computers. This idea that, hey, we are in the midst of inventing something here. And of course, I mentioned the very first computer, the ENIAC, first electronic computer, back in 1945 by Eckert and Mauchly. This was not programmed the way we think of today. It was programmed by plug cables, patch cords, And in fact, there was sort of a division of later. The women were the ones who did the patch cords for it. The men wrote the programs. This is why I think ultimately a woman invented Fortran at some point, or maybe there was some relationship there. Of course, I wasn't around back then, but the first computer I got exposed to is somewhat notable. It's the IBM 1800. The IBM 1800 is a computer, I think it was introduced in 1963. It's related to the IBM 1130. It's a 16-bit computer that has 64K bytes of memory maximum. This model was used for factory control. It was the first real-time computer, quote, real-time computer that IBM made. It had been shipboard at Scripps Institute of Oceanography on a ship. And they decommissioned it and sent it to UC San Diego to live in the chemistry department. And what happened is a very small group of students were given essentially full reign of this computer to use as their, quote, personal computer. We had the ability to write programs, put the programs on. There was a small storage scope that was used as display. And it was a seminal experience for both myself and Bill Atkinson, who later went to Apple, because here was a room-sized computer that was completely at your beck and call. You were the only person using that computer. And you can imagine that this was an unusual circumstance in 1970, 71. Not too many people had personal computers. The folks at Stanford and Sale, ultimately had that same experience, and a few people like Larry Tesler had access to terminals. This was a mind-bending experience to have this computer at your beck and call, and certainly for a 17 or 18-year-old, it tended to set a lot of thinking in directions of, boy, what can you do if you have complete ownership of this computer? That was in complete distinction to the campus at large that did have a mainframe. They had a CDC mainframe and then a Burroughs mainframe, and that was a computer where you went up to a window and you handed off your card deck, and then some number of hours later they handed you a pile of line printer printout, and that was the computing experience. The immediate turnaround from being able to type in your program, have it run, watch the results on a vector display is what I think set us and other people who were being exposed at this time to this kind of environment, who later went into the personal computer industry and said, you can do that with personal computers. Very quickly, the mainframes were replaced in the 70s by mini computers. And the same thing was true at UCSD, where I was working with Bill Atkinson. We had a mini computer, a PDP-11 mini computer from DEC. One of the notable things about it is that it had what's called an orthogonal instruction set. That means that as opposed to earlier computers that were quite complex in their instructions, the instruction set had a small number of registers, 8 registers. They were all treated the same way. You could, in fact, memorize the entire instruction set, and many people did, because there was so much regularity to it. Again, we had this computer pretty much for our own use as undergraduates. There was a fellow there by the name of Kent Wilson who ran the chemistry department who believed that undergraduates could do as interesting research as graduate students if you just sort of turn them loose, especially on computers. One of the aspects of this computer is that it was hooked up to an Evans and Sutherland picture system, which was a 3D vector graphics display. In fact, serial number 1 of the Evans and Sutherland picture system, which came out of Utah, was installed at UC San Diego and became sort of both a research instrument and a toy for some of us undergraduates. And you could write a really mean game of Space War on this thing. One of the notable aspects was that there was a device called a lorgnette wheel, which it was a lorgnette which you would hold up to your eyes with a spinning wheel with 6 discs. And the 6 discs would alternately expose the left eye and the right eye in red, green, and blue, since it was a black and white display. And if you were in a darkened enough room, you could get the illusion of a color 3D display, although it did give you a headache after a while. The sort of chip revolution was churning ahead, and of course in the mid 70s we had the microcomputer. The Altair was mentioned. This is an IMSI 8080, which was an 8080 chip, very reminiscent on its front panel display of that DEC computer. It was not a graphical computer by any means, and in fact, one of the things you had to do after you got your IMSI 8080 was to beg, buy, or steal a cheap teletype, mechanical teletype, to hook up to it. Or if you were really rich, you would get a CRT display with a keyboard. These were not something that it was not a mass market at that time. It was the quote hobbyist market. And to bring us a little bit more up to date, this is a picture of the Apple II. The Apple II is notable because it was an all-in-one design for the keyboard and the power supply and the computer. It came out of the box programmable in BASIC. It had the very beginnings of packaged software on it. VisiCalc had come out, I think, in 1979 with a packaged spreadsheet, and that was sort of a revelation that, boy, you could have a packaged software industry. One of the reasons I showed it with the top off here is that if you pay attention to the memory chips and how they're laid out, and the spacing on those, the spacing on the memory chips is actually the same as the spacing on the other chips on the board. And I'll come back to that in a little bit when we talk about the Macintosh. Now, at the same time as the Apple II was coming out and becoming popular and selling in the low millions, ultimately, as was mentioned in the previous talk, there was a lot going on at SRI and at PARC and a few other places. And this is that same picture of the SRI prototype mouse invented by Doug Engelbart in 1963 or thereabouts. As you'll notice in this photograph, you can see it is absolutely a one-button mouse. Now, what they ultimately commercialized or distributed, and the first mouse I used was the 3-button mouse that you see Doug holding here. And Doug, I think, was once asked how many buttons should a mouse have, and his answer was as many as possible. I'll come back to the mouse and how many buttons it has, because it turns out that's an interesting window into some of the design decisions that ultimately went into the Macintosh computer. But to anyways, zoom out from this overview here on how, what was the environment like in the early days of the Macintosh design. I want to bring up a quote by Jeff Raskin. Jeff Raskin was the original manager of the Macintosh group at Apple, really before it was a Macintosh. The design was very different at that point. He had, I think, what is a correct insight. He says, I think that years from now, when the details have been washed away by the acid rains of time, 4 major commercial events will stand out in the history of personal computers. And he named the microprocessor, packaged software, graphical human interface, and the internet. And we were in the midst of the microprocessor revolution in 1980 when I started at Apple, and the packaged software revolution was just starting. As I mentioned, VisiCalc, I think, came out in 1979. This idea that you could sell packaged software that was a spreadsheet. And in fact, when I first got to Apple, one of the things they showed me was the software applications for the Apple II, which was a file cabinet that one drawer with a bunch of diskettes, which were all of the applications known for the Apple II at the time. A lot of them were freeware. A lot of them were just copied around at the computer clubs. But as I mentioned, some of them were starting to be sold and became what is now the packaged software industry for personal computers. The graphical human interface really did not exist outside of Xerox PARC and things like the Altos and Smalltalk. Very few people had seen it. There was lots of graphics around, but very little graphic human interface that you could interact as the main way of interacting with your computer. And of course, the internet at that point in 1980 did not exist at all. Um, so this brings us up to the Macintosh, and as I mentioned, the work started on the Mac in 79 and 80. The original Macintosh was not a 16-bit chip. It was, in fact, an 8-bit chip. And the design was based on the 6809 processor from Motorola. It was not, in fact, based on a mouse initially. It was graphical. It did have a bitmap screen. It did have an integral. At that point, it had an integral keyboard. The design was a nice one, and actually would have ended up being fairly low cost, but also fairly low performance, especially compared to the other project which was being done at Apple at that time, which was the Lisa project. The Lisa project was based on the 16-bit 68000 processor, and it was meant to be an office computer. It ultimately shipped for a price point of around $10,000, so it clearly was not in the same class as the Apple II and the personal computer. But one of the things that happened during the early 80s was that the graphical user interface for Lisa had evolved quite a bit. There was a low-level graphics package called QuickDraw. At that time, it was called Lisa Draw, that was developed by Bill Atkinson. And I happened to be living at his house at the time while I was working on the Mac project. And rather than having to reinvent all that code or port all that code to the 6809, I thought it would be easier just to base the Mac design on the 68000. And so the other key engineer on the project at the time was the hardware designer for the Mac, Burl Smith. And I went to him with this idea. And the only fly in the ointment was that since the memory chips were 64K by 1 memory chips, if we went to a 16-bit wide bus, we would have to bump the design spec from 64K bits or K bytes to 128K bytes. And back in 1980-81, that would have priced us way out of the market, so that what Burl did is, over one night of wire wrapping, figured out how to make an 8-bit memory bus work with the 68000 using multiplexers and demuxers. And we were able to then convince management, which was basically Steve and the board of Apple, that we should switch to using a 68000 processor.
Hey, Bud?
Yeah.
This is Ed. So what was the internal timeline of the Mac and Lisa project? That is, we know that they were introduced several years apart, but inside the company, when did they start? I believe the Lisa project, which predates me at Apple, started around 79. The Mac project started in 1980. So they were pretty contemporary. The Lisa shipped about a year earlier than the Mac. I think the Lisa shipped in 83 or so. But they were completely two different groups of people. The Macintosh project was actually a very small project initially, less than a dozen people, and was run quite separate from the Lisa group. The Lisa group became fairly large, between 100 and 200 people working on the Lisa project, many of them coming from Xerox PARC. We had one or two people on the Mac team who had come from Xerox PARC. The Mac team ultimately became even more isolated when it became very secretive, and we kind of moved it off campus to a place called Texaco Towers, because it was behind a Texaco gas station. And this sort of isolated it politically a bit from the Lisa group. The other thing is that our philosophy was, I think, more of a hacker philosophy. We're willing to get down and write assembly code for a lot of things just to fit them into the cheaper memory size footprint. Whereas the Lisa team was writing in Pascal. It was fairly, in our minds, verbose code. The actual source code itself was written in something called Hungarian, which is named after Charles, probably named by Charles Simoni or someone around him. Simoni came from Xerox, went to Microsoft ultimately, and invented this idea that every variable name should have embedded in it all the names of the types it is. So if you had a pointer to a handle to an integer, the variable name would start with point, hand, int. And then you'd have about 3 characters left over for the actual variable name. And when you tried to read through this code, you might as well be reading Hungarian. So I think that's where the name Hungarian came from. But the cultures of the two teams ended up being very different. The Mac team internal to Apple was known as sort of a pirate group, off on their own, off in Texaco towers, very secretive. Although we weren't totally secretive, we did have some early visits by Bill Gates and a few of his people. We knew that it was going to be important to attract Microsoft to develop software for the Macintosh. So I think in 82 and 83 we had some visits by Bill, and we went up to Redmond to visit again to try and convince Microsoft to go ahead and make the investment to develop software for the Macintosh, which they ultimately did. I'm going to point out one of the things that happened in the Mac group was an incredible attention to detail. And a lot of this came from Steve, but a lot of it was also just sort of a craftsman-like approach to things that permeated the group. And both the hardware and the software, but the hardware is easier to point out in some cases. So this was a 1981 breadboard for the Macintosh. You can see at that point that the 68000 had replaced the 6809. The memory had actually grown to two rows of memory, so a 16-bit wide memory, 16 by 64K. And an interesting thing is that you can see the memory chips are actually spaced much closer together than the other chips. So they're not laid out on a perfect grid. And if we jump ahead a year, partly due to the influence of Steve Jobs, the memory chips are now laid out in exactly the same grid spacing as the rest of the chips. So this is something no one is ever going to see, but we're going to see it. And this attention to detail really permeated the group and permeated both the software and the hardware design. Some of the design, yeah?
No one is ever going to see it on a Macintosh, but the Apple II had Velcro on its cover, inviting everyone to see it.
That's very true. Yep. In fact, at one point, Apple did make a clear version of the Mac that you could sort of see through. So some of the interesting design issues that were faced. The operating system and the toolbox fit into ROM. There was 128K bytes of ROM space that was used. I think it was initially 64, and it grew to 128. And this is because ROM memory is a lot cheaper than RAM, or was a lot cheaper at that point. And so you could save money by sort of burning your basic operating system and the toolbox, which implemented the graphical user interface, into ROM. There's also an ulterior motive to this. One of the difficult things is to get software developers, especially at that time when we were coming out, to actually write their application using the graphical user interface. Their sort of knee-jerk reaction was to write it using a command line interface, because that's what they were used to doing on MS-DOS or on the Apple II. And by putting this code in ROM, we could make the argument to them that, well, if they just would call our code, that would save them extra space in their own application code memory running out of RAM. And so simply by the argument of you want to have your program run in as small a space as possible, you ought to be using the toolbox that we give you in the ROM, independent of whether a graphical user interface is better, quote, better or not. There was a lot of software, what I call software assist for the hardware. The software operating system got intimately involved in timing for the reading and writing the disk drive. Individual bits were being read in software. And this was all to save 1 or 2 chips on the board, which would translate ultimately into cost savings for the final computer. It was an interesting design decision that we didn't bring out all of the address bits. In fact, the 68000 did not bring out all the address bits for 32-bit address space. They only which would be 4 gigabytes. They only brought out 24 address bits, which meant that your memory maximum would be 16 megabytes. Now, this seemed infinitely large to us at the time, and so one of the things that happened was we started using the upper byte of the address of this 32-bit address for extra flag bits and just extra memory that obviously was never going to be used. It was just lying around, and memory was such a scarce quantity that this seemed like a good idea at the time. This actually caused no end of trouble ultimately because, as we all know, 16 megabytes was ultimately not very much memory on a computer, and so we sort of had to reclaim, or Apple had to reclaim that high order byte in order to make things run properly in larger memory.
Hey, Bud.
Yeah.
So what seems funny about that is that IBM users had already been through that, right? The early 360s only used 24 bits of addressing, and then they moved to 32, and everybody used to use that high order byte for stuff in the 60s and 70s, and they had already fought and lost that battle in some sense.
Yes, it's maybe worth pointing out that so I'm somewhat responsible for this, along with Andy Hertzfeld. And my own personal experience, I'd never programmed in OS 360 or on an IBM 360. I had programmed on the 1800, which was a 16-bit computer with 64 kbytes max, and I'd programmed on the PDP-11, which was also essentially a 16-bit computer. You could segment things and get a few more bits of memory, but that was about it. So my own personal experience, I think, fed into this decision, which was, ultimately a wrong decision. We used a lot of assembler versus, Pascal, which was the primary language on Lisa, to get things fast, but more importantly, to get things small, because we did not have a lot of memory. Everything had to fit ultimately in 128K bytes of RAM. A single floppy disk drive, 400K bytes. The Mac had the first slot load disk drive that Apple worked together with Sony to develop, the hard shell. Prior to that, the disks used in the personal computer industry were the 3.5-inch. They were actually floppy. They had a soft shell case. The Mac was the first computer to have that hard shell case drive. And then finally, no user accessible bus. There was no way to open up a Mac and attach something to it. One of the things that I and others pushed hard for is to provide a knockout panel in the Mac and call it a diagnostic bus, because we knew that at least the hobbyist community would want to knock that out and get to it. But the counter-argument was that the FCC approval would be very difficult for that, and actually having someone hook up to the bus would potentially lead to reliability problems. So ultimately, we went with the all-in-one, no user accessible bus design. As I mentioned, we used QuickDraw, which was the same graphics subsystem used on the Lisa. This is an early dot matrix printout of a screen called MaxSketch Demo. It was written by Bill Atkinson to exercise the graphics, and you see the patterns. It was a black and white computer, so about the best you could do to differentiate things on it was to use these different patterns, and these patterns sort of became a staple of the Macintosh, used a lot of places in software that ended up being pretty ugly and sort of had to be expunged after color came along. It's interesting that there was a huge amount of iteration on this design, trying it out on ourselves and very few others, but mostly trying it out on ourselves. And one of the key requirements for working in the Mac group was to be able to rapidly write new versions of software to try out new ideas. There were no prototyping tools like we have today. If you wanted to try out something, you basically had to write the whole program or most of it and try it out, and a lot of that was going to be assembly coding. In Mac Paint, which was the program where a lot of these ideas got tried out, we had a guy in Bill Atkinson who could literally write thousands of lines of code overnight to try out ideas. And there were dozens of iterations on Mac Paint. Here's a very early version of Mac Paint that someone was I think Steve Capps, who was one of the early Mac people, actually did this drawing in it. Interestingly, there's a command called AIDS. This was in probably 1982 or 83, and AIDS was just being really discovered at that point by the medical community. In fact, when I was a medical student, I had some of the very first patients with AIDS, and we actually had no idea what it was at that time. In any case, in the Ultimate Mac Paint, that menu command got renamed to Goodies, if you've ever used Mac Paint. It's just a miscellaneous menu item. One thing I want to mention is that there was a lot of late night discussions and sort of what I would call deep thinking about the computer-human interface or computer-user interface on the Macintosh. And a lot of this was in the air. Certainly the people at Park were grappling with these issues. But one of the interesting things, this is a picture of Jean Piaget. And he's a psychologist who had this theory of development of the mind, stages of development of the mind. And one of the early stages, I think around year 1, that babies develop is something called object persistence. That means if you have an object and you hide it, the person knows that it's still there and expects, if you move the obstruction, that it will still be there and acts surprised if it's not there. And as I mentioned, children develop this around age 1. There's a few animals who have the ability to know that objects persist. And it was actually a strong driver on the Macintosh, presenting this illusion that the things on the screen are objects which have a lot of the properties that in your most basic neural wiring you expect them to have. That things that when you drag them around stay where you place them. Again, the thought of leveraging off the fact that the human mind is pretty hardwired to know how to retrieve spatial memories of things. Probably comes about because that was one of the ways you survived, by being able to find your food sources again. If you found a tree with berries, you really wanted to be able to go back to that same tree to get those berries. One of the very early iterations of the Finder, what ultimately became the Mac Finder, which was the interface to the file system, sort of took this to an extreme, which would not have been that useful, but we then backed off it. But this is the a Finder where you actually display a floppy disk. This is before we had the hard shell disk from Sony, and you display a floppy disk, and then you actually have a little icon or text image of the name of the file, and you can drag these things around, and and the idea is that you really get the concept, if you're not a computer user at all, that these things exist, these files exist, they are on the disk. If you put them on the disk, they stay where you put them. One of the things about this diagram worth noting is the doit command. The doit command, I believe, came from the Lisa group originally. They used it as the command to do it, which makes sense. And there's often a dialogue with the doit command and a cancel command. One of the big revelations was that this did not go over well with users. And this was actually something, a lot of things were found by testing it out on ourselves, but this was one thing that was found by user testing. When you put something that says do it in front of someone, they actually don't really know what it means. And there was one guy in particular where we videotaped it, and when you played back the videotape, every single time he would not hit the do it button. He would hit the cancel button in that case. And this was very odd until we turned the audio way up on the videotape, and we could hear him muttering under his breath, and he was saying, "Dolt, dolt, dolt," and he'd press cancel. So user testing, which really, the idea of heavy user testing came out of the human factors movements in the 60s. My dad was actually a human factors designer in the NASA Apollo program. But a lot of the guys at Park, Larry Tesler and others, lived and died by user testing, and that propagated itself into the Lisa group and somewhat into the Mac group. I already mentioned design by iteration, incredibly important, especially when the user interface is involved. That's because the human part of that loop is totally unpredictable, as the example of Dolt I recently gave you. So that the user is part of that feedback loop. The best case is when the user is the developer, because that feedback loop is very short. But it's actually the rare person who can be a good proxy for your average user. I actually think it was a skill that some people had, some people didn't have. A lot of the people on the Mac group actually had that. And then finally, the importance of taste and good design. And as I'll come back to, a lot of that comes from Steve Jobs.
Question from San Diego.
Just a few words about the user interface. Of course, it was graphical. It was the first commercialized graphical user interface. One way of thinking about that is all systems up to that point have been command line interfaces, all commercial systems. And in a command line interface, you're faced with a blank screen and you have to type. And that's sort of like an essay test. Whereas the graphical user interface was a lot more like a multiple choice test. You had all the answers there, and all you had to do was choose one. And that's the fundamental underlying principle of why graphical user interfaces are easier to use, or one of the key things. We also invented the idea of the menu bar at the top, the pull-down menu. These came out of the Lisa and the Mac. No modes. Larry Tesler had a T-shirt that said, "Don't mode me in." And the idea here was that there should be no modes, that all of the commands you could do at any one time should be visible on the screen. You shouldn't have to get into a different mode to do a different command. One-button mouse requires a bit of mention. The idea there is really that it's optimized for learning how to use the computer by watching somebody else use it. If you think about someone using a computer with a two-button mouse, they may in fact be more efficient, but the guy who's watching him do something and expects to learn how to do it has no idea whether they're pushing left mouse button or right mouse button. So it's really a question of what are you optimizing for. Since nobody in the world, to a first approximation, knew anything about graphical user interfaces, there was a lot of optimizing towards easy to learn versus efficient to use once you've already learned it. I think an even more important principle in the Mac user interface design was the idea of learning by exploring. That you should be able to sit there and just poke around at the system, and there should be things that sort of grab your attention and make you poke on them, and you should never feel like you shouldn't poke on something. This led to the concept of undo, for example. The undo was implemented by the Lisa group to be the full, you can undo everything you can do. The Mac group backed off and said, we'll do one level undo. If you do something and you want to back out one level, you can. You can't keep undoing after that. Again, with the memory constraints, that was about all we could do. Interestingly, the Star, which shipped out of Xerox, didn't implement undo at all. They had an undo key, but you couldn't do an undo. This is a great example of when you look at the Star and you see that undo button, you go, well, of course, undo is a great idea. And we didn't understand that the Xerox people found it too hard to do undo. So we went ahead and did it anyway. We didn't understand that it was too hard to do. Another example of this is that when Bill Atkinson initially saw the Smalltalk overlapping windows, he thought that you could, as a programmer, draw into any window, even draw into windows that were behind other windows. Well, it turns out on the Alto and on Smalltalk, you can't do that. You can only draw into the frontmost window because that's the easy programming problem. But Bill didn't know that. He thought, how are you going to make it draw into the back window? Because that's probably what the guys at Xerox are doing. And he actually invented something called regions, which was a way to graphically draw in windows that were behind other windows, because he didn't know any better. He didn't know that really smart people had looked at that and decided that was too hard to do, we'll just paint into the front window. A lot of examples of things like that. So ultimately, the Mac shipped in 1984. This is what the Mac user interface looked like at that point. One of the key things that happened subsequent to that is that there was a three-way deadly combination or killer combination, which was the Macintosh with the graphical user interface and WYSIWYG word processing for the masses, combined with Adobe inventing a PostScript printer in conjunction with Apple that was cheap enough for at least offices and businesses to buy, combined with Aldus PageMaker, which was an application for doing this paste up on the computer, so you could do desktop user publishing, desktop publishing. Desktop publishing drove not only Mac sales, but drove a lot of the industry for a long time, and was really only made possible by the fact that you had this combination of three things: graphical user interface, cheap laser printers, and applications like Aldus PageMaker. Now, in 1985, I'm going to do a time check here.
30 is the official end.
When's the official end?
9:30.
9:30. Okay, great.
Whatever works.
So to shift gears a little bit, in 1985, a year or so after the Macintosh shipped, Steve Jobs left Apple. And ultimately, 5 of us, including myself, left Apple with him to form a company called Next Computer. And the original idea behind Next, Steve had spent the summer talking to people like Paul Berg at Stanford and gotten really interested in higher education. So the initial idea for Next was to build a computer for higher education. In fact, a group of people in higher education had written sort of a blueprint for what would the dream computer be in higher education. They call it the 3M machine, which meant that it would have 1 million bytes of memory, run at 1 MIP, 1 million instructions per second, and have 1 million pixels on the screen, a megapixel display. And in their minds, this was the perfect computer. And so computers at that time were really not very near that. A typical, well, the initial Mac that shipped was 128K of RAM and a 400K floppy disk. Ultimately, you might be able to get a larger screen on it, but I think the screens didn't get over around 600 by 480 for quite a while. So this was a bit of a reach, but we were very interested in reaching, and the higher education goals were very attractive, and Steve was able to bring this group of people from Apple over to Next, and it was a little bit of a rocky start. Initially, Apple sued the company for sort of taking these people away from Apple, but very quickly Apple found it was not a good idea to sue your founder. It led to a lot of headlines you don't want to see in the press, and that eventually went away, and we got started in earnest. An interesting thing that happened, one of the first sort of field trips we made, Steve asked us to show up the next day and get on a plane to Pittsburgh, Pennsylvania. We had no idea what this was for, but he said he wanted to set the company on the right path initially. And so we showed up, we got in Pittsburgh, and we drove about 2 hours out of town to a place called Falling Water. So we had all 6 of us, the whole company, basically, at Falling Water. And Falling Water is sort of it's an architectural masterpiece by Frank Lloyd Wright, and with the epitome of beauty and craftsmanship. And we spent the better part of a day touring through the house and looking at all the details in Falling Water. And then we flew back to California. That is probably unusual for a company to do at its founding, but it really gives you an insight into some of the things that drove Steve Jobs that had to do with aesthetics, with design, with craftsmanship. All those things were present in the Mac group and really got transferred into the Next culture. You see here the design of the Next as it ultimately came out. The hardware design was a cube, 12 inches by 12 inches by 12 inches. It actually met or exceeded the 3M specs, with the exception of the screen, which was not quite a megapixel, but it was close. This is a very early shot of the very first Next Step user interface. It's a few of the notable things. It had multimedia email. You can't really see it very well, but this is a little picture of lips in there. It actually, you could make a recording, and there was this feature called lip service. So you could speak into your mail message, and that message would get recorded and be a pair of lips, and whoever received that would see lips, and when they clipped it, would play back your message. The screen itself was, interestingly, it was grayscale, and there were only 2 bits, so you could have 4 different values. You could have black, light gray, dark gray, and white. And those were represented by a 2-bit value on the screen. And this was a compromise. It was a compromise because I and some others insisted that we have more than 1 bits. There's a saying in computer science that there's only 3 numbers, 0, 1, and many. And because if you go beyond 0 and 1 and go to 2, 3, 4, 5, 6, etc., there's a whole set of problems you have to solve. And the same is true with graphics. Once you commit to having more than 1 bit per pixel, there's a lot of things that a lot of problems you have to solve that will stand you in good stead when someday you can do 8 bits or someday you can do 32 bits with millions of colors. And this was exactly the reason for doing 2 bits. It was a little bit more expensive, but it really drove the software design in a number of ways that made it very easy to quickly move on to color once that became cheap enough to do. Next step was a combination of CMU Mach, which was a microkernel, plus Berkeley standard distribution Unix, so the Berkeley flavor of Unix, which is called 4.3 at that point. Those were melded into the plumbing, the operating system for Next Step. Interesting story, we used the GNU GCC compiler. So open source was just getting started at that point. Richard Stallman had an Emacs application, an editing application that he was distributing under the copyleft. And the GNU group had a compiler. And the price was right for us. It was free, although it came under this copyleft license. To us, it seems totally natural because Berkeley Unix at that time was also being distributed more or less for free, and it had a long history going back to the 60s of being distributed for free. So free software didn't seem like that big a deal to us. There was a meeting at some point between Steve Jobs and Richard Stallman that was sort of, I don't think a whole lot of communication took place. But we did end up using the GNU compiler, and we had what's called Objective-C, an Objective-C front end on that to add some object-oriented constructs, which were well proven in the Smalltalk world. But to us, the idea of using that together with C seemed like a good combination. The display was built on Display PostScript, which we developed with Adobe. And the idea was that if you're going to do WYSIWYG, what you see is what you get, then your very graphic primitives should be the same ones that you're using on the printer. And there really wasn't enough processing power to do that in the Mac or any previous computer. But with the next computer and this 3M idea, you finally had enough processing power, if you were clever, to make PostScript really the graphical primitives. Then you have zero mismatch between what you see on the screen and what ultimately gets printed out. The Next Step GUI was overlapping windows, had a more multimedia feel to it with things like lip service, and sound actually became a very important part of the computer. Interface Builder was a tool that had not been seen before. It was beyond compilers. It was how do you build a graphical user interface using drag and drop, using the graphical interface itself. And Interface Builder really did an excellent job of that. Ultimately, it led to a lot of derivative work that is very similar to that, building GUIs with GUIs. But at the time, it was sort of a revelation to people. Many other things packaged onto the computer, as I mentioned, multimedia email. Interestingly, we included the Webster's Dictionary and the complete works of William Shakespeare. Now, that would not have made any sense at all if the internet and the web existed, because you can find these things on the internet today. But at the time, it being an educational computer, and we had some space on the disk. We actually had a pretty large disk, as I'll get into. Mathematica, the first version of Mathematica by Stephen Wolfram, was actually written for the NeXT computer and shipped with the NeXT computer. There was something called Godzilla by a fellow, Richard Crandall, who essentially, I find it to be one of the first examples of grid computing. If you had a network of NeXT computers, you could actually send jobs to them all, and when no one was doing anything, any typing or mousing on the computer, it would actually work on that background job. As soon as you touched a key or moved the mouse, it would stop doing that and pay attention to you. But it actually allowed you to corral a lot of computers on the network to solve problems. And I think one of the things Richard did is at some point he had either one of the largest primes or a similar math problem that the NeXT computer network at NeXT itself had solved. MusicKit, done in conjunction with Karma at Stanford, a very extensive ability to simulate instruments using physical simulation. And there was a DSP, which was a Motorola 56,000 part, which was an attached processor that was extremely good and fast at signal processing, and that was used in the sound and music subsystem. FrameMaker initially came out as a word processing program, so it was a very complete system. It all shipped on a read-write optical disk, which was, I think, the first read-write optical disk on a workstation or computer. It was a 256 megabyte disk, which again seemed to us huge enough to just throw on the complete works of Shakespeare and the Webster's Dictionary. One of the problems was that this was the only disk, and it was extremely slow. So we had to actually do a lot of innovative things with the paging system and virtual memory. You could also only write to the disk so many times, which was a problem for virtual memory. And it turns out that this did not last too long. Pretty quickly, as a follow-on product, NeXT came out with a version of the computer that had a hard disk drive in it as well. One of the interesting things about the NeXT computer is that it got in the hands of a lot of smart people. And you could imagine, that's pretty natural. It's aimed at higher education and research, and that's exactly what happened. Well, one place it ended up was CERN in the hands of Tim Berners-Lee. And he used it to write essentially what became the World Wide Web. And I remember at one point he actually showed this to us and to some other people at NeXT, demoing what is essentially the World Wide Web with one problem. The World Wide Web did not exist at that point. And so we looked at it and we said, well, who really wants to look at documents at CERN? Because that's all you could look at. That was the extent of the web at that point, was the research documents at CERN. But luckily, it became ported to other systems, and when the rest, as we say, is history. But at one of the World Wide Web conferences last, I think in the late 90s, they actually had the NeXT Cube, where he had written the World Wide Web enshrined in a plexiglass case, showing this is where the web was born. Interestingly, the browser he initially wrote was not a read-only browser, it was a read-write browser. So it was both a browser and an editor. It's interesting that the Netscape browser that came out of Mosaic was a read-only browser, so it kind of left behind that ability to edit the web, which has come back now recently with the wiki. But there's, if you think about it, one of the things that didn't exist in the original browser was any sort of notion of bookmarks, because if your browser can also be an editor, you would never think of wanting to have bookmarks. You would just have a page with all of your links on it that you were interested in. Those are your bookmarks. So the whole concept of bookmarks becomes unnecessary if you have a read-write browser. So I think the NeXT computer in this and Mathematica and many other ways ended up having a pretty large impact on the world. But beyond that, This is towards the end of Next's existence, because Next, when Steve Jobs came back to Apple, one of the things he did was acquire the company Next along with NextStep and all of its software. And this is a screenshot of NextStep sort of around that time, and you can see someone had written an email message that sort of talked about Apple and Next merging. One of the outcomes of that was not only some of the people merging into Apple, but some of the technology as well. And really, the operating system that the Mac used from Mac OS 1 through Mac OS 9, version 9, was a pretty unbroken stream. There was probably even some bits of code that were still in there at that point. The architecture was pretty much the same. There was some multitasking added and higher 32-bit pointers and things like that. But Mac OS 10 became really a pretty complete break from that lineage, in that it switched over to being Unix-based. In fact, Mach and BSD Unix-based, like NextStep was. And of course, with Mac OS 10, which is actually denoted with the Roman numeral 10, a lot of the user interface changed as well. Just a couple of brief words on open source. And open source is both a software development methodology and a religion. And the two sides don't always talk to each other on the same terms. But actually, the software development methodology was one of the first things that struck me when open source really started taking off. Of course, I had been exposed to it back with Richard Stallman, so I got the whole religious part of it as well. And a lot of that came out of the Berkeley Unix culture as well. But this idea that you could have a large number of people working on code all around the world and in real time on internet relay chat and all working on the same source tree was just a revelation. At the time, I had been away at Sun Microsystems for about 7 years, and one of the holy grails for the software, the formal software development community, was follow the sun, what was called follow the sun development, where you could have tools and networks so that you could have people in India and Australia and the U.S. and Europe all working on software 24/7 as the sun went around. No one was ever able to make this work very well. Some people have claimed to, but what actually does work is open source, and this is what you see as just the normal course of development using open source methodology, people from multiple continents all working on the same source tree, all communicating on the internet, and somehow it just works. And I think it actually manages to, at least a little bit, break Brooks' law. In the Mythical Man Month, Fred Brooks, who developed IBM OS 360, said that complexity and communication costs of a project rise with the square of the number of developers, while the work done only rises linearly. And this quickly, as you get beyond 7 programmers, means that your complexity and communication kills a project. And I can only imagine what's happening in Microsoft and other places with huge projects. Brooks' Law will just kill you. And on the other hand, with open source, it's interesting. They seem to somehow avoid, and I'm not sure exactly how, but this phenomenon to me seems real, that they somehow avoid Brooks' Law for a while. And it's probably worth someone studying it and finding out why that is. Just quickly, the history of Mac OS 10 and some of the contributions and influences that went into it. We start back with Bell Labs Unix in the 60s. Of course, that led to a whole variety of flavors of Unix. The one that ended up being used in NextStep was 4.2 BSD out of Berkeley, along with CMU's microkernel. Those came together in NextStep. That was ultimately ported to other platforms like Sun, Spark, and Intel in the form of OpenStep. And ultimately, as I said, Next was acquired, and that technology got folded into Mac OS 10. And of course, a lot of the influence, especially with the user interface, came down from Mac OS 1 through 9 as well. And then finally, the underpinnings, rather than the Berkeley standard distribution, Apple uses something called FreeBSD as the basis for its underlying Unix, and that actually is a derivative of Berkeley Unix. So just an interesting family tree there of sort of all the pieces that came together in Mac OS 10. Here's a recent screenshot. I think this is the Mac OS 10.4, which is our most recent shipping version. And some of the next influences, the next machine came up with a dock. The whole sort of multimedia feel, I feel that at least the next culture really encouraged that. Of course, Apple had QuickTime and a lot of that culture as well, but it's really come to fruition with the Mac OS 10. Here's an interesting slide. It's hard to see the top there. I don't know why it didn't come out well, but it's comparing the 1984 Macintosh specs with the typical specs of a Mac computer in 2006. And here you can see CPU speeded up quite a bit, and roughly a factor of 300 there. That lets us do a lot of things like display PostScript that we, or PostScript graphical primitives, and now even more complex graphical primitives that we couldn't do before. RAM, of course, has gone way beyond the 128K, a factor of 8,000. But the real story to me is if you look at disk drive, which is, at least if you start at the 400 kilobyte, it's a factor of 200,000. But even if you start at something like 5 megabyte, which was the size of the first hard disk for personal computers on the market, you get a huge factor in storage. And I think that that's actually one of the big challenges of fully utilizing computers today. One of the things that we noticed a few releases ago was that it was easier to find stuff on the web than it was to find stuff on your own hard disk. And there's something wrong with that. And so one of the things we did is introduce a technology called Spotlight, which is basically searching for your own hard disk, full text search, inverted index search for your own hard disk. It's kept continually up to date as you add and remove and edit files on your disk. But I think utilizing that storage properly, and more importantly, how do you back it up is one of the big challenges. Still, no one backs up their hard disk. The other challenge, yeah.
Sorry, can I go back and ask another open source question?
Sure.
So I'm interested in roughly what the size of your OS group is. My impression is it's pretty small compared to what we in Seattle are used to. And I wonder how open source relates to that, and to what extent is OS 10 refreshed from open source, and to what extent did you snapshot open source and you're holding the bag for carrying it forward?
Sure. Well, so open source code is an evolving code body, and in my opinion, it's actually not useful. It's not very useful unless you yourself or you have programmers who are involved in the community that's developing that project. I think there's really, it's almost impossible in my mind to actually snapshot something and use it, because the knowledge that's embodied in source code is not by any way, shape, or form formalized. It's why Knuth call it the art of computer programming. You really can't take a steaming pile of code from someone else and do anything useful with it, is a shorthand way of putting that. So what that means is that for the open source projects that are in Mac OS 10, we, as much as possible, have our own programmers involved in the community developing that code. So, FreeBSD itself, we participate and interact heavily with those guys. Things like Kerberos, that would be a huge team if we had to write that from scratch. But the folks at MIT are, and the whole community around Kerberos is doing that. But we have people on our team who who are also part of that community. And I think maintaining that live connection is absolutely key to being able to use open source at all in any sort of project. Roughly, probably half the lines of code that we ship are open source, and about half the lines are proprietary source. The proprietary source tends to be graphical user interface related code, as well as application code, things like iTunes. And I personally believe that it's very difficult in the open source community to develop anything that has that user really closely inserted in the feedback loop. That would include graphical user interfaces, and that would include applications, consumer applications like iTunes or iPhoto. And I think those things are actually best done by very small groups, tight-knit groups of people who can develop a design language and a design schema and communicate that to each other really every day during development. Having a large distributed group of people develop a GUI, I think, leads to too much of a phenomenon of every good idea gets thrown in, and you don't end up with, I don't know, you don't end up with falling water, you end up with Mexico City or something like that.
Thanks.
As I mentioned, you know, these are large projects. They only work if you break them up into components, but all of these systems today, Mac OS 10, Vista, Linux, are on the order of 10 to the 8th lines of code, somewhere between 10 million lines and 100 million lines, maybe 50 million lines of code in that range. That's a lot of code to sling around. We never could even imagine that in the early Mac days. We didn't have the tools to do that. To some extent, we sort of have the tools to sling around this much code, but I'm not sure that we have the cognitive sense to really understand what's going on. I think it remains a challenge and will continue to remain a challenge for things like program correctness, you know, the number of bugs per line, the security issues that come up. There's no magic bullet around this. This is you can't read this. It's not meant to be read. What you're meant to see on this is that this is when the initial Mac shipped, and of course Apple continued to develop derivatives of this product line. And you can see that at a certain point there was an awful lot of different versions of the Macintosh. This is just the hardware products that are shipping. And interestingly, from this diagram, you can see when Steve Jobs came back to Apple. And one of the key things he did, Apple was, you know, in tough straits business-wise financially at that point. One of the key things he did was to simplify the product lines and to simply say we're going to stop doing a bunch of stuff. For example, that's when the Newton went away. I think that was a key event in Apple's history, and this idea of keeping things simple, though, really goes back to the company's roots and the company's culture. And I think, you know, I'll have a few examples of that later on. I'm not going to spend too much time on this because of time, but it is notable that this has become a mobile world, and this isn't unstoppable. This is actually an old graph. This is from '04, but and this is students entering into colleges and universities and what they have with them, laptops versus desktops. And this trend is actually even more pronounced today. And this is where a lot of our current efforts are aimed at, you know, in this mobile world. And you can look at the iPod as another example of that. I'm going to skip that for time. And I will do these three slides. The culture at Apple, a lot of it does emanate from Steve, but a lot of it at this point is institutionalized very heavily into the company. And he was asked by Business Week in 2004, how do you systematize innovation? And I think his answer is a good reflection of what actually goes on at Apple. He says, the system is that there is no system. That doesn't mean we don't have a process. Apple is a very disciplined company. We have great processes, but that's not what it's about. Process makes you more efficient, but it doesn't help you. But innovation comes from people meeting up in the hallways or calling each other at 10:30 at night with a new idea, or because they realize something that shoots holes in how we've been thinking about a problem. It's ad hoc meetings of 6 people called by someone who thinks he has figured out the coolest new thing ever and who wants to know what other people think of his idea. And that is what drove the early Mac group, and I think that is what continues to drive Apple today. In fact, drives, I think, a lot of the open source culture and hacker culture as well. And this is a key one. Innovation comes from saying no to 1,000 things and to make sure we don't get on the wrong track or try to do too much. And any successful open source project has someone who's really good at saying no, for example. And that slide that showed the product lineup and what happened when Steve came back is a good example of saying no, and the concept that sort of less is more. And a sort of graphical graphical representation of this. This is Apple's design for remote control versus the a different design for remote control from Microsoft. and you know, our idea was that go back to first principles and you know what you want to, if what you want to do is watch a show, why are you typing in numbers to your TV? And why not leverage what goes on the screen to make that process a lot simpler? And you know, of course, features sometimes get left out when you do this, but that concept of knowing when to say no is an important one. Again, making applications simpler. These are little dashboard widgets that are going back to breaking up applications into smaller pieces, making them simpler. These are actually based on Web 2.0 type technology, JavaScript and HTML. Another bringing you up to current directions we're thinking in, again, making things simpler. This is something called front row. It's the idea that if you're using your computer to consume media, to sit in your living room and watch your TV, you really have to, even the desktop metaphor is way too complex. And we're not alone in thinking of this, but Apple's approach to this is really, I think, baked into the company culture and stands us in good stead when we do things like design iPod user interfaces or front row. And finally, the other idea or thread that remains at Apple is this idea of integrating things together. I could talk about iTunes and iPod being integrated together, but we're still continuing the trend here. The flat panel screen is integrated with with the actual computer, so that the computer is actually in the lower part and back behind the screen. Another notable thing is that the camera is now integrated. If you can integrate a camera into every phone, why shouldn't you have a camera integrated into every computer? Okay, well, I'm going to stop there and see if there's any questions.
UW?
Questions up here?
Yeah.
Shout it out.
When you were working on Next, right at the beginning, were you using Macintoshes to do that work?
No, we were actually using Sun Microsystem workstations. I mean, I'm sure we did some word processing on a Mac.
Shout it out.
Yeah, another one from UW. I was wondering, too, on the Mac and also at Next, you mentioned PostScript as something that was highly leveraged. And then I was wondering with OS 7, when TrueType was integrated with the Mac platform, and how did that was like compatible with but not dependent upon PostScript, right? And then how did that impact the relationship with Adobe and also the users of the desktop publishing?
Yeah, well, that's interesting. That was during a time that I was actually at Next. Actually, I might have been at Sun Microsystems at that point, but I was not at Apple. So I can't speak to Apple internally. It was clear externally that there was a lot of, tension between, which was actually always there, the tension between Adobe and Apple, as well as, intense collaboration and synergy. And I think in the case of typefaces, that was a situation where Apple went for a while in their own direction. But since I wasn't there, I probably can't talk directly to your question.
Well, Bud, was there a cost issue? I mean, I remember the PostScript interpreters used to be really expensive, and I remember that the Next laser printer was remarkably inexpensive because you used the PostScript driver that was in the machine to drive the printer. The printer didn't have another.
Yes, well, that was partly, I mean, the cost issue was absolutely both the software and hardware amortized across both the workstation and the printer. So the printer was a dumb printer. It was like a dumb dot matrix printer. There was no PostScript inside the printer. Since we already had PostScript running for the display, it was very easy to reuse that same code to do the printing work and to just spit it out to the printer instead of the screen. So it was cost savings on both the hardware and the software.
Did you guys have font designers at Apple?
Absolutely. In the early Mac days, there really were no. Well, I don't want to say there were no bitmap fonts, but there were no good typographically designed bitmap fonts at that point. The bitmap fonts actually were an evolution from the 7-segment LED displays, and when they figured out how to put more LEDs in dots, and they invented dot matrix printers, they came up with some bitmap fonts. But we actually had a group at Apple that Susan Kerr was one of the lead designers there, who came up with the typography and the bitmap fonts that were in Mac. And I think Apple's continued for some time after that to do their own fonts. At this point, we don't do our own fonts for the most part because there's such a huge font industry out there doing fonts. And they're no longer bitmap, they're now spline fonts.
Microsoft.
Yeah. One comment, Falling Water leaked horrifically.
Oh, yes.
But for my question, I'm wondering whether the Scully time at Apple, I know you weren't there, was that a good thing for Apple to get a break in the reality distortion field that Jobs had? Or would Apple be light years ahead if Jobs had never left, if you had never left?
Well, of course, that question is impossible to answer. I was there for a very brief time when Scully was there. Steve actually hired Scully into the company. I think the question you're asking, was it good for the company to take a break from Steve? I think that it might have been good for Steve to take a break from the company.
One of the first things that Scully did was raise the price of the Mac, which must have, to pay for marketing, which if I were on the team, I probably would have been a little insulted.
Oh, well, certainly I think a lot of decisions would have been different with different management. I do think price point was a key issue in what happened with the Mac versus the PC. It's not clear that competing on price, directly competing on price with the PC would have been a winning strategy. Even so, because of course the PC was taking advantage of the horizontal disintegration of the industry and manufacturing, and the Mac continued to be manufactured by Apple. So, was that a good decision? In retrospect, I think it didn't work out very well.
San Diego?
Yeah, I got a question. Can you hear me over there?
Yeah, go ahead.
You can? Okay. You mentioned on the quotes about innovation. Basically,
Yes, we have a question from our other speaker.
Oh, wait a sec. Hey, Steve?
Yeah?
San Diego's asking a question, but you can't hear them. So, San Diego, why don't you ask the question and I'll repeat it, okay?
Thanks.
Okay. It's going to be a little different. On the quotes about the innovation part, basically
Is it going to be the same question they asked?
Basically seemed like you were talking about lack of structure there at Apple. And My question is Apple ISO certified or anything? Because I know they have the standards or anything like CMMI.
It'll be a three-word question.
So I'll do the best I can with this.
Yeah, please.
Yeah. So the quotes about innovation from Steve, it spoke to sort of lack of structure, and the question was, is Apple ISO certified or something like that?
Well, I think it actually spoke about lack of a system, not lack of structure. In fact, he talked about process being very important. So ISO is a process-oriented thing and doesn't have to do with, what's your system to innovate. It has to do with you have process to do it efficiently. And Apple has ISO 9000 for manufacturing and things like that. We have common criteria process for our software security. So there's a lot of process there. But when you start to talk about what's the system, can you systematize innovation? That's, I think, a different question. And I think Steve's answer is correct, that there is not really a way to do that. I don't know, maybe there's a drug that can do that. but we, I don't think anyone really thinks they've systematized. If you did that, that would be augmentation.
How big is the company now? How many heads?
That's a question.
I think we're the better part of 20,000. The company has grown in headcount tremendously due to opening retail stores. So we have, I think, on the order of 150 retail stores around the world, and all of those are staffed by Apple employees.
Ed, can you shuttle some more?
Yeah, is there another San Diego question? Go ahead.
Yeah, one more San Diego question. I've been very impressed with Apple's commitment to computing for people with disabilities, and I'm interested in hearing more about the story behind that within Apple, their commitment to people with disabilities and computing.
So, Bud, the question is, the person who spoke has been very impressed with Apple's commitment to computing for people with disabilities and is interested in hearing more about that thread, where that commitment arose from and what sustains it.
Mm-hmm. Well, I think that's been a thread at Apple. I know that, so I've been back at Apple for 5 years now, and it was also, it's something that's been one of my interests, and I've been pushing in my capacity for it. Ultimately, it widens your market, and it also pushes you in directions that I think end up sparking ideas that are good for the entire population as well. So I also think that at this point in time, at least for a lot of the standard things you do on computer, there's really no excuse not to do it. There's plenty of processing power. The architectures we have support it pretty well. So I think there could potentially be a problem in it becoming too highly regulated. In other words, there's a temptation by some governments, because not everything is accessible, to legislate. And I think what that does is squeeze the innovation out of this, because I actually don't think we've done all the innovation necessary to make everything accessible, and to try and write down the rules for accessibility at this point would be way premature. But pushing for it in general is something I do.
All right, so we're a little bit past the mark. Thank you for everybody for staying, and thank you for the speakers for putting up with our and giving such fine talks.
Bud, thank you, and John, too. Thanks.